Welcome everyone. We are still missing some people, but I think because it's a full day, they will come and leave during the day. So I'm Fausto Gallucci from OneCube, and I will chair this workshop or meeting, if you want. The meeting is organized and supported by 6 projects. You see the names here. They are related to the technologies used for ammonia. Some projects working on ammonia production, some projects on ammonia cracking, some projects just on separation. But they have all in common that are European projects that want to disseminate the results. And of course, normally for scientific results is easy because we go to conferences. This meeting is not just about scientific results. You will see presentation more on perhaps helicopter view on the problem. We have presentation from industry, and we have time for discussion. So that is the most important. So the projects are Amber, Andrea, and Apollo. They are related to ammonia production, Amber, and cracking, Andrea and Apollo. Then we have Caipirinha. So because of the name, we will not select the best name because they will win for sure. Then we have Faster and Measured. So as I said, these are all European projects. We have the coordinators here. So during the day, there will be presentation from industry. Then there will be the coordinators giving a short speech, and then they are open for a chat with you. So prepare already the questions. And later we will have presentations more for from the projects. What else? We have quite a lot of people online, so I hope that they will join all. We have almost 200 registration online. For the people online, of course, we will share the presentations. We will share also the video that we are doing. So if everything goes okay, by next week, everything will be online and can be used. And you can find in all the projects websites. Good. What we did as well, we have lunch today. Everything is offered by the project. We have lunch. There will be tables where the coordinators are. So please do not micromix. Do not stay in your community, but micromix and go to the coordinators, sit together, discuss about the projects. Some coordinators also brought material, so you can check. And then later today in the afternoon, when we finish, there is also a borrow. So some drinks, again, time for discussion with the coordinators. And for this, I think for me is enough to start with. We have the first presentation is online. Unfortunately, we have Dr. Skevis that couldn't come for a personal reason, but he's online. Can you hear us online? Let me see if I can stop sharing.
Can you hear me now?
Yes, we can. Can you share your presentation?
Sure. Let me see that all works fine.
Yes, we see the presentation. So Dr. Skevis is a general manager of Kleos, is part of Caipirinha project. And the company is working on decarbonization of maritime industry. So it's very much related to ammonia. And the company is also working on industrial application of this technology. Dr. Skevis is a mechanical engineer by training and has also a PhD in combustion chemistry from Imperial College. So, Dr. Skevis, you can start with the presentation.
Thank you very much, Fausto. And again, I apologize for not being there. And it was some very serious family health issues. And I also apologize the Caipirinha project because I was supposed to bring all the, the roll-up and all the material for Caipirinha, which you unfortunately missed now. So I'm very sorry about this. In any case, I'm very happy to, and thanks to the organizers and the Caipirinha project to present this work. And let me give you just, I will try to be extremely quick on who Kleos is and what it's doing. So Kleos is a relatively new company. It's been established almost 3 years ago. It's a joint collaboration between 3 big Greek shipping companies. And what we do with something in between R&D, innovation, consulting. So essentially, we're trying to find solutions, soft solutions, hard solutions, develop solutions that will decarbonize initially our fleet. When I say fleet, the fleet of the shareholders, and eventually move forward to third parties, but at the same time retain the operational capability and the energy efficiency. Now, okay. Yeah, okay. Can you see it? Yes, you can see it. Yeah. Now, before I move on to ammonia, let me give you a very general and concise outlook on the specifics of maritime industry. So maritime industry at this moment represents something like between 2.5 and 3% of the global CO2 emissions. This may seem low, but the key is that the maritime industry is transporting virtually everything worldwide. So something like 85% of the trade is going through vessels. This means that there's a lot of visibility there. Every product essentially carries the CO2 generated by the shipping sector. So there's a strong pressure to decarbonize. Not only from outside bodies, as you will see in the next presentation, from regulatory bodies, etc., but also from within the industry and also from financing institutions. Okay. Now, of course, all these things are open to, are very, sensitive to the overall geopolitical framework. Okay, I don't want to go into any politics today, although this is very prominent in this part of industry. But just to say that at this stage, we have a complex regulatory landscape where some regions, like the EU, through the FuelEU Maritime, do have, you will see again the next slide, do have some very strict and well-defined regulations on CO2 emissions and a penalty and reward mechanism. But shipping is, as I said, an international business. It goes mainly into international waters, where in international waters, everything is controlled by IMO, the International Maritime Organization, a UN organization, where things are not running very smoothly or going sometimes in circles due to political situations. Now, if we leave regulation and politics aside, we have many other significant barriers to the decarbonization. Traditionally, shipping was a very conservative and low-tech industry. So introducing new solutions, either in terms of new technologies or in terms of different fuels, is challenging, to put it that way. And ammonia, of course, is even more challenging, but we'll go to that later. So even solutions that work on land, like, for example, waste heat recovery or other similar solutions, they have to be redesigned. They have to be marinized, as we say in the jargon, to work on board. Okay. Now, the health and safety is always important, but on board a vessel that is traveling in the middle of the ocean with the next land about 1,000 miles away, it's even more crucial. Okay. And also very crucial is the training of the crew, the perception of the crew, the perception of the captain. The captain is king. So everything has to be taken into account. I go to the last point, which is very important, then I will end up with the complexity of the industry. So ships, of course, travel, but they start and end somewhere. So particularly when talking about fuels and onboard carbon capture, which I'm not going to speak at all today, the land infrastructure is important. So we need to have bunkering stations. We need to have loading and offloading stations. These are work for heavy fuel oil, for the typical marine fuel, but are not generally there for other fuels. And the final thing is the complexity of the industry. There's not one shipping industry. A big tanker going to from the Persian Gulf to East Asia is a totally different story from a ferry or an inland vessel, etc. And also who own, and also you have a series of players, as I said, the ship owner, the operator, the charterer, etc., that have different interests that have to be satisfied at the same time. So it's a complex thing, everything that an R&D company and an R&D world wants to have, right? So, okay, let's jump directly to ammonia. And why do we need ammonia? Why do we consider ammonia? Okay, we know it's a very low quality, it's highly toxic, it's unsafe to handle, etc., etc. As you can see, I have put here some print screens from different sites in the last couple of weeks. Okay, it's the most dangerous fuel shipping has ever tried to bunker, but at the same time, things are happening. So where do we stand? Okay, of course, the first and foremost criteria for adopting ammonia is that it's carbon neutral, or rather can be carbon neutral if we take in a well-to-wake approach. Okay, it is a commodity. Okay, it's a commodity for as a gray or brown or whatever color that is. I will show you again the next slide, but at least the infrastructure is there. So the problems I mentioned in my previous slide about land infrastructure, backing facilities, etc., is not that difficult in the case of ammonia. And also the last one is if this, of course, goes on for all non-fossil fuels, we can produce it locally, and that we don't have to rely on 2 or 3 areas across the globe. This means that, the security of supply is higher. On the other hand, it's a very bad fuel. You have to admit that. Okay. Combustion is poor. Emission characteristics, I was having second thoughts when I wrote that. Okay. So, okay, let's say they're different. We need new engines. It's not a drop-in fuel, like biofuels, for example. Health and safety is very crucial, particularly so for onboard applications. And of course, there's always cost and availability. But again, one would say this is a common theme on all new and e-fuels. Now, let's start from regulation, because as I said in the beginning, people will not pay if they're not obliged to, okay? So we have in this graph here on the left, I have summarized, rather somebody has summarized for me, but I'm copying it here, the current situation on regulation. Okay, now this is the carbon intensity, so grams of CO2 per megajoule, and this is the, as we say, the trajectory over the next 25 years. Okay. And this is, as a base case, we're taking this 91 point something, the carbon intensity of heavy fuel, but essentially the carbon intensity of all hydrocarbon fuel, okay? Liquid hydrocarbon fuels used in the industry. Okay, and as you can see, we have this is the fuel EU, this gray line is the fuel EU maritime, so it's the requirements by the EU, and as you can see, they're pretty mild for the first 5 years, up to 2035. Essentially, you can leave without doing too many changes, but just some changes in efficiency, etc. or moving to a better combustion, etc. But then after 2035, definitely after 2040, things accelerate. So I won't spend much time on the IMO curves because these are still under discussion. And but just to say two things: they're even more steep than fuel U, and the penalties are much higher. Okay. And the final line to take into account is this zero or near zero carbon fuels. This is essentially a mechanism. If you go to very low carbon intensities, and as you can see, these carbon intensities correspond to green ammonia as well, also to green methanol, etc., then you have additional financial rewards. So people will always take this, at least the fuel EU trajectory, very much into account when they go into considering the new fuel for the application. Okay, now, as we said before, and as you very well know, I'm not an ammonia expert. Ammonia is a kind of split personality, right? I mean, if ammonia is produced, if the hydrogen for ammonia, etc., if ammonia is produced from fossil fuel, then it's totally it's one of the worst fuels in terms of carbon intensity. Okay, so you can see gray ammonia up to 150, brown ammonia up to 100 to 120. Now, things change when you go to blue ammonia, for example, where you're talking about steam reforming and carbon capture. Then you have values that are typical, similar to say, a first generation biodiesel. Okay. But not good enough. So if you compare this to that, it's good enough for, say, up to 2030, 2040, but then it's not very good. And of course, if you go to green ammonia, then these intensities are very low, and they can be a safe alternative fuel. Now, the problem is, of course, on the balance of what we have and what we need. This is the ammonia production for 2025. Okay, and as you can see, only a very small fraction of that is coming currently is currently green. Okay, now this is not the problem for me. The problem is this graph here, where it shows you the capacity up to 2030. So there's a projected capacity. Again, I don't want to go into that, and the details, of course, may change anytime. But the thing is, if you take even the most optimistic projection for blue and green ammonia, then you're talking about some like 15, perhaps 10% of the current production. Okay, so this is something that definitely needs to be to speed up. Okay, so let's keep these numbers in mind. Now let's go to the more difficult part of the equation, which is how much do we need? Now ammonia, the shipping sector operates almost in its entirety on heavy fuel oil. Some like 98%, 99%, but around 98 to 99% of the vessels, of the seagoing, the merchant vessels, those that are more than 5,000 tons, etc., operate on heavy fuel oil. And we consume roughly 300 megatons. Now, if you suppose that you're going to change into, say, green ammonia, these are just scenarios, right? And use this to cover 35% of the energy needs, take into account that ammonia has roughly half of the heating value of the fossil fuels, then you're talking that you will need some like 200 megatons. So that's more than what we currently have. Not green, everything. Okay. And of course, it's also a question of how much hydrogen we need to produce this. So without going into the numbers, this is a difficult exercise. Okay. And understandably, as you can see also in these projections, the ammonia, the shipping sector is projected to be the biggest user of ammonia in the next period, but still we need to find these quantities. But you also need to build the boats, right? And as you can see, because big merchant vessels have a lifetime of 20, 25 years, So for vessels that are built in the next couple of years, these will last up to 2050. And as you can see, there are not that many. So it's both chicken and egg and wait and see. So this is the landscape. On the plus side, of course, we have a very good knowledge on bunkering, transportation, etc. Right? The ammonia is generally transported by vessels, of course, not run on ammonia, run on heavy fuel oil, but still we have the bunkering ports. We know how to handle ammonia as a cargo at sea. I will spend one slide on this in the end of my presentation. And we have the vessels to transport it. This means that we know the technology of how to either liquefy it or compress it or do a combination to carry. So this is the easy bit. Now, let's move again to the difficult bits as a fuel. Okay, there are more experts in this meeting on combustion of ammonia, but just to give a very short summary and focus on on engines. So we know that ammonia is okay. Now flammability limits, okay, that's not the biggest of the problems. It has a very high autoignition temperature compared to diesel, but the key problem here is it is a very slow burning. You see 10 times less than diesel. And this means that when you're talking about, so the combination of this low reactivity and very high autoignition means that when you go to burn it in compression ignition, diesel engines, which are all the engines in the in merchant vessels, then you need very high compression ratios, which you don't find. So what means is that you need two things. You need a diesel or a diesel-like pilot fuel, and then you need optimized control and engine redesign. That's why you're moving to new engines. On the plus side, big two-stroke marine engines are very, very low speed. The typical speed is around 50 RPM. Okay, so there's residence time enough to combust ammonia. It's getting more challenging for stroke engines. I will show you later. This is, I intended to skip this just a little bit. If I spend something like half a minute here, is to show that, okay, ammonia may be a bad fuel, but as you can see, not much worse than fuels like methanol, for example. So you can see that, typical energy density, typical autoignition temperature with LNG. But again, so it's not a disastrous, but the thing is here, it's very slow burning. Now, the other thing is a volumetric density, volumetric energy density. Okay, if you compare, if you take your reference case, the fuel that is currently used, this HFO or MGO, this is the heavy fuel, this is the marine diesel. Okay, you can see that you need something like 3 times the cargo space for storing the same energy quantity of ammonia. This is not land, this is ship, and the ships transport things. So even 10% increase in decrease in cargo space to use it as a fuel tank, it's crucial. So this is a big problem. On the other side, it's on a par to methanol, and it's much better than hydrogen. So definitely a low energy, slow burning, relatively bad fuel, but in some respects much better than hydrogen. Now, going into emissions, I'm not saying definitely that it's worse than hydrocarbon fuels, but definitely different. There's no CO2 on a tank-to-wake approach. Okay, so you don't release any CO2 on board, and there's no SOx and there's no PM. So this is good. You have 2 key problems. The first one is this fugitive NH3 emissions. So it's like methane sleep, although ammonia is not a potent GHG agent. But the thing is that you have releases everywhere. And this is a problem because ammonia is toxic. More to that later. Now, on NOx, again, there is a controversy. You have two competing trends. I mean, you have lower temperatures, so you're going to reduce NOx because of the lower temperatures, and you have fuel-bound nitrogen, so it's going to reduce NOx from the N in the ammonia atom. But again, we have the technologies to mitigate that. Wait for a couple of slides more. And of course, you have N2O, which is extremely potent DHG gas. But again, with the right tuning of the engine, this can be reduced. Now, okay, so let's see where we stand at the moment. I would say, again, as I said before, chicken and egg, wait and see, but some things are happening. But and we are actually at the center of the things that are happening right now. For example, and I will spend a bit more time on those three cases. Generally, large shipping engines are produced by two manufacturers, WinGD and MAN, which has now been renamed to Everlance. So Everlance is rather WinGD already has a two-stroke engine we're running on ammonia, and is installing it in this EXMAR vessel and is expected to be commercial by the end of the year. MAN Everlance is slightly lagging behind, but still it's the first commercial engine has also been completed, and there is Varsula, which has completed four-stroke engines. So we have first of a kind cases in all key engines. Let me go a little bit on those. First of all, let me point out that all these engines are dual fuel. Dual fuel means do not make a distinction between dual fuel and pilot fuel. It's not clear to everybody. Dual fuel means that the same engine can operate in two different fuels, in two different modes. So one day can operate on ammonia, the next day can operate on diesel. Okay. Even when it operates on ammonia, you would need some diesel or similar fuel to ignite it. Okay. Both two-stroke engines operate on what we say a high pressure mode, which means that the fuel is injected directly into the compressor and ignited by the pilot. Why do they do this? Because they have stable combustion, there's lower ammonia slip, but at the same time you have to be you have to handle high pressure lines, which may be a problem. I won't spend too much time here. The same principle is also by MAN Everlance. Now, the one thing to note here is, have a look at this graph on the left. But these are the engine efficiencies. You can see that. Okay, I don't know whether this is actually. Don't take this at the extreme face value. But the takeaway message here is that diesel mode and ammonia mode on the same engines have very similar efficiencies. And ammonia may even has higher efficiency. So in excess of 50%, which is very, very good. Now, if we go to four-stroke engines, things are not that. First of all, why use four-stroke engines? Vessels have very high electric needs, so they use smaller engines. That you see, these are of the order of a few. Oops, mistake here. I'm sorry. These are megawatts, right? So they use gensets, as we call them, auxiliary engines, generators of a few megawatts, compared to the, say, 20, 30, or 40 megawatt of the two-stroke engines. Okay, so again, this is engines that has been developed in the last couple of years and is being actually available and in the process of being installed on board. So we have also a four-stroke engine to play around. You can see, of course, thermal efficiencies are lower, but this is typical of four-stroke engines have lower efficiency than two-stroke engines. And ammonia slip is more difficult here because of the higher residence times, etc., etc. So you need after treatment, but this is something you will always need. Now, as I said, even if you build the best ammonia engine, the problem is not the combustion of ammonia. The problem is how you handle it and the fuel supply lines. Okay. The good thing is from the combination of ammonia as a cargo, our experience in cryogenic technologies for LNG, and the emerging cryogenic technology for hydrogen CO2, we have a lot of experience of how to store those things. Okay. Now, I mentioned at the beginning that storing ammonia as a fuel is different than storing ammonia as a cargo. Why? Because ammonia as a cargo is aqueous ammonia, is a emulsion with water. It has only 28%, typically less than 28% concentration. As a fuel, we need, of course, a high purity. Okay, and so this changes a little bit the things. And this is interesting. I didn't actually know that, but I found when I was doing the presentation that ammonia is recognized as a fuel only for 1 year, last year. Okay, December 24. This means that we now have in place practices to store it as a fuel. And bear in mind, if there are no practices, either from IMO or from Garcia societies, a ship owner will not take the step to install it on board. Okay, if I'm running late, I only have 2 slides. Okay, you need specialized tanks, etc. But I think these are material problems. I'm not saying that they're not there, but I'm saying that these are currently solved. And the most serious problem is the handling. High toxicity, low viscosity means we need double wall piping. All this increase the cost. It's not only the technology is there, but the cost is increased. And also, things that we do not have with, not even with methane, we have a lot of fugitive emissions. Okay, ammonia may leak from several places. It's not only the ammonia going down out of the engine, it's also ammonia can build up in the boiler room, in the engine room. So you need water spray systems, etc. You also need to worry a lot about dispersion, and you have to redesign. That's another issue. You have to redesign the deck. You have to redesign parts of the vessel to make sure that the ammonia releases, which are generally going out through a vent mast, as you can see here, are not going towards the personnel accommodation quarters, etc. And what do we do about emission control? I think I'm running late, right? If I'm running late, yes. Let's go to the last
2 minutes more.
slide. Huh? Sorry, how much do I have?
2 minutes more.
Okay, so let's go to the last essential slide. Emission control strategy is a very, very big part. Again, we have here we combine experience from LNG carriers and, of course, heavy fuel carriers, and we have 2 issues here. One relates to the fugitive acid emissions, the ammonia slip in the on the pipe, etc. And what we do there, again, straight coming from LNG technology, we either have a boil of gas manner, so we liquefy the ammonia emissions and put them back in the tank, or we have a dedicated small GCU, as we say, a gas combustion unit, where it burns off this ammonia before it enters the main engine. And of course, we have a combination of SCR, where it is good because ammonia is an agent for SCR, so we can use the fugitive ammonia to promote the NOx reactions, and also an ammonia slip catalyst. Okay, this may seem straightforward for a chemical engineer. It seems extremely complicated for a naval engineer, and of course adds up to the cost. And that's my last slide. I'm not having any conclusions, to be honest, because you see, it's all open questions, and I think workshops like this serve to show us the way and how we can proceed. The only thing I want to point out here is that in parallel with retrofitting, with using ammonia in two-stroke and four-stroke engine technology, people are also looking at different things. These are very recent. This is not that recent, but this involves a company, this thing here, yes. One of Claire's shareholders, Gaslog, which was working, at least in principle, on ammonia gas turbine for one of its LNG carriers. This is not a marine application, but things are progressing in ammonia gas turbines, and this is also maybe a plausible option for things on board. And of course, we have all these nice technologies of ammonia cracking and how ammonia can be used to promote the hydrogen combustion, for which we know more, although not necessarily better or safer. And this is what this workshop is all about, or some of it is all about. Okay, so thank you very much. Thank you for giving me the space to talk about those things, and I'm very happy if there is time to answer questions. Thank you.
Thank you very much. Thank you very much. Right. Is there any question? Yes, please, Kevin.
So Kevin, another illustration. So you mentioned a lot of the potential emissions. Would you be able to quantify how ammonia engines would compare to other engines in terms of emission performance? And what then would be the implications on the SCR, emission mitigation, that kind of thing?
Probably, let me share again. Probably I went very quick on that. Okay, so yeah, so you can see here. Yeah, here we are. So first of all, there's no, as we said, there's no hydrocarbon, there's no SOx, so there's no PM, etc. You can see that, first of all, it all depends on load and engine. And this kind of, this is focused, this slide here is only for two-stroke engines. You could expect the first four-stroke engines are worse, okay? But this also goes for the other type of fuels. Now, you can see that for a typical, but this is for the MAN engine, and also we do not have much information, right? Because we only have a couple of engines. So you can see for the MAN engine, the NOx values are definitely better, and I think this is due to the low temperatures. And this is the actual released ammonia. Okay, after the after-treatment system, okay. And you can see it is below this 10 ppm limit, which is proposed. It's not, I don't think it's a regulation yet, but you're talking about a few ppm, right? So overall, I would say that with the current state of the art of the optimized two-stroke engines, we are below in NOx. And released ammonia is less than the limits. 30 ppm, if I'm not wrong, is the safety limit for no actual health effects, etc. I don't know if that covers you.
Yeah. There is another question. Let's see. Yeah, you, Antonio.
For this nice presentation. Looking to the future or other potential application of ammonia, I would like to know what is your feeling about direct use of ammonia in a solid oxide fuel cell or partial cracker system integrated with the solid oxide fuel cell. Which is your opinion on and this kind of technology can be used instead of direct combustion? Thank you.
Yeah. Okay. It's a very big issue, as you would expect. If I am to talk about, say, maritime applications, you mentioned SOFCs and you mentioned ammonia cracking to hydrogen. Let me start for the last one. There are pros and cons, I understand, for ammonia cracking to hydrogen. As I briefly said in my last slide, first of all, we know how to handle ammonia as a cargo. Okay, so carrying ammonia and using this to produce hydrogen, and then using hydrogen either as an additive to the diesel fuel or the methane fuel, or using for a fuel cell, is a much more well-known technology. Okay, it removes two of the big uncertainties, rather, which relate to the storage of ammonia and to the new engines. So in that respect, it's positive. On the other hand, one has to know something I didn't mention at all in this presentation. There's no time. Is the overall energetics. If we're talking again about maritime applications, the ship energy system, the energy available, although we're talking about, say, 20, 30, 40 megawatts, these are all for propulsion. Okay, so the energy system is optimized. There's not much free energy around. So we need to see how much process like, say, cracking, what is the energy requirements and how they're going to fit into the vessel. And thirdly, I'm not convinced. I was more convinced before I started preparing this presentation. I'm slightly less convinced that hydrogen is a better fuel than ammonia overall. And the final thing about fuel cells, well, here you're talking about three unknowns. First of all, you're talking about how fuels ammonia will operate in SOFCs. You're talking about the issues of the high temperature of the SOFCs, which is, again, for heat integration, is very difficult. And you're talking, the third thing, I think it's clear, a fuel cell is has advantages as an auxiliary electricity generator on board. So again, I cannot say, of course, you would expect a yes or no. I would say that both issues are very important to further investigate. But take into account overall the energy system of the vessel. That's the most important thing.
Thank you very much. In view of time, if you have any other question, you can always put in the chat. Thank you again for the presentation.
Thank you, Fausto.
Now, let me see if I'm able. The next one.
Try to switch to the second slide.
Yes, I will. It's my pleasure to give the words finally to Dr. Uribe. He's from the port of Rotterdam, and for us, working on ammonia is also a reference because many of the innovation on ammonia are taking place in ports or close to ports. So it's very important to have your view here. And Duna is manager of new energy portfolio, hydrogen, ammonia, and all these kind of technologies. And she is also passionate about net zero and something that is important for all of our projects, that is gender equality is very important. Okay, so we lost a little bit of time, but please.
Thank you. Thank you very much. Thank you for the invitation. I'm Dr. Fausto, and I should stay on this side of the room,
You
right?
can stay any.
Over here. Okay. So good morning, all. It's extremely intimidating to be presenting to a very academic and very knowledgeable audience, and I'm definitely not a doctor, so far from it. I'm talking from the business side of things, and I hope that I'll bring an overview of what's happening at the port of Rotterdam, and I would like to get just a hint of who has been to the port of Rotterdam, just so I have a reference here. Okay, so some of you, not most. Okay. So therefore, I bring some numbers, worked when I do it, it doesn't. Can you change the slide? Anyhow, so I'm working on the new energies team, and we have a huge challenge at the Port of Rotterdam. So if we look at, well, the Port of Rotterdam was once the world's biggest port. Nowadays, we are Europe's biggest port, and that's because we've been overtaken by the Asians, especially the Chinese. No surprise there. That's where a lot of the trade is happening. But what is important, and I'd like to highlight, is this number over here. 13% of the total EU energy consumption goes through the Port of Rotterdam. What are these cargoes nowadays? This is about coal, this is about oil, and this is about gas. And it feeds not only the cluster, the industrial cluster that takes place in Rotterdam in terms of refineries, petrochemicals, but it also feeds the hinterland. Because as we say, Port of Rotterdam is Germany's biggest port, because that's our biggest hinterland. We feed into their steel mill plants, for example. So the coal goes over there, the iron ore goes over there, just to give some examples. So how do we, so large port, out of about 30,000 vessels call a year, many barges. The whole European Union is basically our market, 500 million people. But how do we then decarbonize all of this flows? Therefore, we have a strategy which is very much aligned to the European ambitions. We aim to be net zero by 2050 and cut that more than half, very aligned with the Fit for 55 European targets by 2030. But that's extremely challenging because we're not talking about the Port Authority. The Port Authority has, 1,000 employees, 1,200. It has some patrol vessels around the harbor, but we don't own molecules. We don't import coal. We lease terrain and we receive vessels that from companies that do that trade. So we need to work alongside with them to ensure and motivate and stimulate that they will be decarbonizing, because together we need this whole ecosystem to decarbonize. And therefore, we are focusing on the energy transition, which is basically pillars 1 and 2, but also the feedstock transition, because it's not only about energy in terms of fuel, but it's also about different feedstocks that you will use for actual industrial processing. So it's actually 2 transitions at the same time. And then I'd like to bring in hydrogen, because ammonia for us stems from our hydrogen ambitions. The European Union has a very ambitious hydrogen goal, which is basically to produce internally in the EU 10 million tons of hydrogen and to import 10 million tons of hydrogen. And that's all by 2030. Now, there has been a lot published already. You're not going to hear from me as the first one telling you that most likely these goals will be revised, because these are, they have been proven to be too ambitious for what has been delivered so far. However, that doesn't take our ambition to move towards that goal. That doesn't take it away. So if we translated the European goals into what we could have at the port, and basically, there's a lot of information, but I'm gonna cut it short for you. We need to be importing, we need local production of hydrogen as well, and those are actually going quite well. There are quite a lot of subsidies. So Shell is building their electrolyzer plant. Air Liquide has started construction, so some good news over there about, and I'm talking about green hydrogen production in Rotterdam. But we also need to import, because what this graph shows is that over here is local production in the Netherlands and the EU, but overall, most of it will have to be imported from other sources in Europe, from other sources globally. And the nice thing, especially with the situation in the geopolitical framework that we find ourselves in, is that the hydrogen ambitions allow us to be more diversified in terms of supplies. So going back to the import of hydrogen, we need to have about 0.7 to 1.7. So let's say two scenarios there by 2030 of imported hydrogen. But we don't, how do we import hydrogen? How do you put hydrogen in a vessel? We just talked about ammonia as a vessel fuel, but how do you actually transport hydrogen? Well, you need carriers. And therefore, we have several carriers. We are a large port, so we are not making any choices as one or the other, but we are looking into serving all types of carriers for hydrogen. So then clean ammonia is definitely one of the most important ones. And why that is because, and I think the previous speaker also touched upon that, is because we have existing infrastructure. There's 200 million tons of ammonia being traded, and 200 million tons of ammonia produced, excuse me, and 20 million tons traded in the world by vessels. So there's already trade internationally taking place, and that means vessels moving, storage, logistics being available for that. But we also have the other carriers that we're looking at. Methanol, very important for SAF production, if we want to have production of liquid hydrogen, very much in a feasibility stage at this point. And LOHC, liquid organic hydrogen carrier, which also can use a lot of existing infrastructure. So I'm going to drill down on ammonia because that's the focus of today and what we're doing at Port of Rotterdam and what we're not doing. So if we look into the whole value chain of ammonia, what is in the white arrows on the left, is what we see that will take place or is already taking place in terms of constructions of ammonia production, and should I say green ammonia production or renewable ammonia production elsewhere, where the energy cost, renewable energy cost is much more competitive. So then when you have ammonia being used by a renewable source, at the moment that you're transporting that ammonia and it's coming into Europe, that's when we as Rotterdam would have a scope in that, right? So then we need storage terminals to be ready to receive that ammonia. And I showed you that there is one terminal already there, that's OCI, which has been bought yesterday. They just closed the transaction by a fertilizer company called Agrofert. And then that ammonia being received here will be either taken to the hinterland in different modalities for use as ammonia per se, and what could the applications be? I think that was one of the questions. What we see studies and we see that in Asia is being used as power generation. Of course, in the chemical industry, which is already a component of the industry, shipping fuel at the port, but it can also be cracked and used as a hydrogen. That's why we're looking at it as a hydrogen carrier. So when we look into hydrogen markets, and those are other markets or additional markets than the ones mentioned here, for example, can be used in the steel plants, then you can also have ammonia as a vector to take the hydrogen. That's when the cracking technologies, which I believe are in the room, become relevant, because then that's how you make that ammonia that is imported from a cheaper production source be available for hydrogen. Right. So then what do we focus on, and what are the pre-requirements or the conditions that need for what I just described, that value chain, to take place in Rotterdam, and to be honest, worldwide? We focus on the 3 A's. So available, affordable, and allowed. And I'll start with allowed, because that's also a lot of what the previous speaker focused on. It's about safety. Ammonia being a toxic molecule, it has a lot of resistance in Rotterdam, to be very honest, and therefore the safety guidelines need to be very, very good and very stringent to be able to have that handling being done at a larger scale. It is already being done in Rotterdam, and that will be very clear. So we handle about 500,000 tons of ammonia through the OCI terminal that's used for the chemical industry and fertilizer industry. But we're talking about a huge volume increase. Therefore, we need safety. So how are we going to ship that ammonia elsewhere from Rotterdam into barges, into rail cars, into the internet? So that needs to be, for sure, to be all there. We have a specific methodology. You guys focus a lot on TRLs, of course, technology readiness level. We focus on port readiness level. So that is our methodology for getting ready for bunkering fuels, and ammonia as a bunkering fuel follows this methodology. I'll speak a little bit about it later on. Availability, is the technology there? Are the molecules there? Are the production taking? Is the production taking place? Where will it be at scale? And in order for us to receive the production, as I mentioned before, we need the infrastructure to be there. So great that we have one terminal, but we need more if that's really going to happen. So this availability needs to be there. And I'm confident that these two will take place. And then what is the key issue at this point is affordability. So where is the business case? This is, if you are in any business setting discussion, it's all about, can the business case turn blue or green? So can it be blue in the sense of positive colors, positive numbers, not of the color of ammonia. So do we have incentive regulations? Do we have subsidies to help with the ramp up period? Or do we price CO2 correctly, etc. So this is very much a key point in order for any of all of this to take place and to be feasible, therefore. So I already mentioned that we're not going to produce ammonia in Rotterdam. We're going to be importing that ammonia. We are going to produce hydrogen locally. So we need the rest of the world. We need countries, locations that have proven competitive renewable energy. And therefore, together with the Dutch government, we have pretty much scouted the whole world as to where could there be interesting and locations for producing hydrogen carriers. And this is what we have come up with. And we are involved in a port in Brazil, in the northeast of Brazil, where we also have shares in Oman, and we have a management agreement in Canada. So that's why they have different colors. But anyways, this is to show how it's really coming from everywhere, and that diversity of supplies is what becomes quite key for the new period that we're getting. Right, so what is the ecosystem? Once it arrives, those molecules arrive Rotterdam. So I mentioned to you that we have the local production also taking place, so it's not all imports. This is the schematic map of the port of Rotterdam. It's 42 kilometers. The city center of Rotterdam is here, and you will go westwards 42 kilometers, and then you reach the Maasvlakte area, which is this area. Port activities take place all throughout that area. And right over here at the tip of the Maasvlakte 2 is where the conversion park is located. Conversion park is where it's basically a cluster of electrolyzers. And why there? Because this is the landing area for where the offshore wind will arrive. So offshore wind will power that electrolyzers capacity, making hydrogen here, green hydrogen. That green hydrogen will then go into the high network. That's the hydrogen backbone. So that's a pipeline. It's already constructed. Actually, they are now already testing it. And why do we need a pipeline here? Because the big idea and the ambition is that companies located throughout Rotterdam and later on throughout the hinterland will use that hydrogen. And once we have hydrogen import via ammonia, for example, it will come into import terminals, and some of them will crack it and then also inject it into that pipeline. So the distribution part of that ammonia value chain or hydrogen value chain is extremely important so that you're actually able to get that molecule to the end consumer. And the end consumer being a big refinery in Rotterdam or being a glass manufacturer in Germany, in the Netherlands. And I mentioned that to the hinterland in the future. So the white line is actually the continuation of that pipeline that I mentioned. And this is all project. So the backbone that I mentioned in Rotterdam, that is constructed. But this one is all project, and this is being done by Haslum, the gas distributor of the country of the Netherlands. And the whole idea is that ultimately you will be connected, the whole Europe will be connected as we are today with fossil fuels. So we will have clean hydrogen in those pipelines connecting different sources or different user types, as far as aviation, refineries, steel plants, etc., and bunkering, of course, in Rotterdam. In addition to the pipeline, the hydrogen pipeline, I think it's very good to show that we're also, in one of the strengths of Rotterdam is the inland navigation, right? So barges are actually our strength, and inland navigation is actually our strength. So it's also seen that before that pipeline is completely there constructed, which timeline now is about 2032, that we will have ammonia transported in barges, which already takes place, by the way, to chemicals, where the companies are producing fertilizers and chemicals. But then you can even go as far as Germany, Ludwigshafen, for example, as a potential off-taking location, and then having local cracking take place. And that is so the cracking can be done either in Rotterdam, and actually I say either, but it's also end, because this is the cracking taking place that will take place in Rotterdam will be large scale. And the cracking that could take place elsewhere in the hinterland could be very much focused on a smaller industrial cluster or smaller even consumer. And of course, rail is also a possibility for distribution. And I also wanted to show that we did so talking about application of ammonia at the port. Then, of course, bunkering. So fuels using ammonia as bunker fuel is, of course, a focus area for us. So in order to simulate that and to actually do to prove that that could be done, last year we have performed a ammonia bunkering pilot. So what happened there is actually about a year ago, so in April. Two gas carriers that were calling the port of Rotterdam. We made sure that they would be at the port at the simultaneous time. And basically, they did a ship-to-ship operation. So they handled ammonia from one vessel to the other. Why is that? Why wasn't it a bunkering, an actual bunkering to the bunker room of the vessel? Because there is no the engines aren't ready, right? So there are no commercial vessels already at this time completely ready. There are some coming on later this year, and there are other smaller vessels that are indeed they are ready and already sailing, but there's no commercial available vessels for us to do that pilot. So we did it as a ship to ship, as if it were a bunkering. So all of the guidelines took place, followed the bunkering guidelines. And this means that this was liquid ammonia or refrigerated ammonia. So we want to stimulate that we have transportation for the hinterland in gas forms or in warm state, not refrigerated ammonia. But for vessels that are ocean going, they're actually shipped at -33, as we saw at the previous presentation. So we also want the bunkering to be done at that, in that shape. And yeah, what can I say here? It was the first ammonia bunkering operation done at terminal. There were other ones that took place outside the port. There's a huge safety element in this. So QRAs were done to ensure that all of the radios alongside this operation, the people would be properly informed about what to do and also what kind of equipment to have. Also the crew and the people that were connecting the hoses for this operation had to have monitors that showed if there was any emission levels, and the ppm of any kind of a slip of ammonia was very low threshold. I believe it was 10 of the max. So very stringent situation in order for this to be done in a successful way, meaning in a safe way. And the idea or the plan forward is that after this pilot, that we can, with the next vessels that will be ready on a commercial scale, that we can do it in a project basis. And which that means that there is no dedicated infrastructure for bunkering, meaning there is no barge that is today available to bunker ammonia vessels. But perhaps in an intermediary phase, we're going to have LPG carriers serving us an ammonia bunker infrastructure to load that ammonia into the receiving vessel. Many partners were very much involved to make it happen. That was it for me. I do expect to get some questions because I've made it quite short and speedy so that
Yeah.
there will be space for that.
Thank you very much.